faculty and students for a very special day, Senior Design Project Presentations. It's a special day for our seniors because I guess on Monday you can start to relax. Yes. I'm just kidding. It's a special day for me because actually today I am no longer your coach and I will ask difficult questions. No, I'm kidding. But faculty will. This is expected. So a few words about Senior Design Project. Is a 2-semester effort. During the first semester, students search for the project, they do research, write proposal, and defend proposal. Then, by the end of the semester, they actually work on a design and deliver design document. The second semester is devoted to implementation and, I guess, a lot of testing. Yes? Yeah. Okay. Today is actually the final accumulating point, presentations. A few words about organization. We have very busy day today, 14 presentations, so please, as I ask you, you have to be on time, you have to finish your presentation on time. You have 20 minutes, actually 15 minutes for a presentation, 5 minutes for questions. And I have to enforce it, so please, I'm sitting in front and watch me from time to time. I will show you 5-minute sign, 1-minute sign, and I think I don't need to use this one. So, yeah, but because of the day, very long, we have to actually allocate only 20 minutes max for a single presentation. So without further ado, please first introduce yourself. Oh, and please, speak loud.
Good afternoon, ladies and gentlemen. My name is Kurt Gibel, and these are my colleagues, Nick Hannon, Sam Cook, and Travis Krammes, and we are Skynet Development Team. Nearly 1,000 service members of our armed forces have returned from Iraq and Afghanistan with amputations. This fact alone leaves families in despair and individuals impaired in their abilities of everyday life as they no longer have a limb that they can use. But there is a solution. This solution is prosthetics. Prosthetics vary on broad band of technologies, from low-tech arms that are just wood that are placeholders where an arm used to be, or a metal hook that can use for simple grabbing tasks, all the way to the complicated deck arm, which uses expensive and high-tech motors and servos to move the arm and mimic the movements and characteristics of an actual human arm. Our solution is the Terminator arm, which uses shape memory alloy technology as a means for actuation for all of our joints. Now you may ask, why are we using shape memory alloy instead of servos or motors? Well, that's simple. Shape memory alloys are light, small, silent in operation, and they're very, very strong. How strong? An SMA wire is about the same width and diameter as human hair, but it can operate at powers of about 7.85 pounds during actuation. SMAs are also very smart. When heat is applied to the alloy, it begins to actuate and shrink in size, as is a wire, and provides all the actuation force as it does so. After it begins to cool, it remembers its original shape and stretches back out to the full length and size of its starting position. SMAs are also very fast. Complete actuation of our joints from 0 degrees to 9 degrees happened at 0.71 seconds on a 50% duty cycle. Shape memory alloys also are very lightweight, only weighing about 1.3 grams, and again, the size, down to the size of a human hair at approximately 508 micrometers. But again, it's such a small and lightweight package, we're getting about 7.8 pounds of force. With that amount of force put on the end of a human finger, if I was an amputee, I would be happy to go to my friends and say, I'll be back. Now to my associate Nick for how this amazing technology is controlled.
Good afternoon, everyone. I'm Today I'm going to be going over the SMA actuator design and our control system. Our actuator consists of 5 basic parts: rotational axis, a metal finger, SMA wire 1, SMA wire 2, and a flex resistor. Our finger rotates from 0 to 90 degrees and capable of stopping anywhere in between. Actuation is controlled by applying a 24-volt pulse width modulated signal to SMA1 to control the rotation of the finger, and an SMA2 to reverse rotation. The voltage drop is also applied across the flex resistor, which increases our accuracy of an angled range. So we can hold, there's 3 modes of operation from our circuit. There's actuation, reverse actuation, and a hold in place. It can hold in anywhere between 0 degrees and 90 degrees. To actuate, we apply a pulse width modulated signal to SMA1, which brings the finger down. To reverse actuate, we apply a pulse width modulated signal to SMA2, which reverses actuation. To hold in place, it's a little bit more complicated. We start actuation as normal on SMA1, which brings it down to the desired angle. If the angle right off of the flex resistor is greater than the angle to actuate, we apply a pulse width modulated signal to SMA2. If the angle is less than the desired angle, we apply a pulse width modulated signal to SMA1. All the angles are read off of the flex resistor and decoded by the microcontroller. To hold in place, we continually oscillate between SMA1 and SMA2 to hold in position. Here's our system. We have a microcontroller, a buffer control circuit, a voltage gate amplifier, and the rotational drum. The input is done by the keypad, where we implement slow, medium, and fast operation, and the angle desired. The microcontroller outputs a 3.3 volt pulse modulated signal to a buffer control circuit, which isolates the microcontroller from any feedback from the voltage gate amplifier. The buffer controller outputs an isolated 3.3 volt pulse modulated signal to the voltage gate amplifier. The voltage gate amplifier sends the 3.3 volt pulse width modulated signal to a 24 volt pulse width modulated signal, which is enough to actuate the SMA wire. MSP, the microcontroller reads the change in value off of the flex resistor and loops through the system to continually actuate our finger. Now, Sam Cook will talk about testing.
In our design, there were 5 main units that needed testing. That includes the pulse width modulation scheme, our flex resistor used for the feedback, the shape memory alloy which makes the actuator, our switching circuit which provides the necessary power, and our analog to digital conversion unit. To test the pulse width modulation, we used 2 simple tests to confirm we were getting the expected output. First, we just hooked up an LED to the PWM output, and the higher the duty cycle, the brighter the LED would show. The second test was simply hooking up to an oscilloscope and viewing the frequency, duty cycle, and voltage range to make sure it was expected values. The next test was for the flex resistor. We had to make sure that we understood the relationship between the angle bend of the resistor and the resistance value we were getting so we could use it as a feedback element. In order to do this, we constructed a rig which allowed us to, at very controlled intervals, bend the resistor and measure the resistance. We found that the resistance gave us about a 10% change between its straight and 90 degrees, so that was the range we had to work with for our ADC. The amplifier circuit, once it was built, had to be tested to make sure we were getting the proper gain and that the MOSFET was switching between power and off. In order to do this, after the circuit was constructed, we initially tested it on a trainer board using the function generator as a square wave, which would mimic a 50% duty cycle PWM, and also using the low current DC power supply in the trainer board first to make sure we didn't burn anything up. After that was confirmed working, we then used the same PWM from the trainer board, but used our DC battery to ensure that our circuit could handle the current without breaking. Once all this was confirmed, we could then hook it up to the actuator. The analog to digital conversion testing was done after we knew the values for the flex resistor. What this involved was after programming it into the microcontroller, we had a panel open on the computer interfacing with the microcontroller so we could read out the values that we were getting. Once we knew the range of these values, we could make our code accordingly to give us our feedback.